Students, good evening. Today I am going to solve a problem. The problem is a small water pump located 15 meter down in a well takes water in at 283 degree Kelvin 90 kilopascal at a rate of 1.5 kg per second. The exit line of pump is a pipe of 40 mm in diameter. Pipe diameter is given. That goes up to a receiving tank, maintaining a pressure of 400 kilopascal gauge. kPa 400 kilopascal gauge. Assume that the process to be adiabatic. The same inlet and exit velocities, exit velocities and entering velocities are same. Water stays at a temperature of 283 degree Kelvin. Density of water at 283 degree Kelvin is found to be 1000 kg per meter cube. The question is find the pump work required. The data given are a pump is installed below the earth in a well. The depth of the well is 15 meter. So del Z, that means Z2 minus Z1 is 15 meter is given in your question paper. The pipe used to pump the liquid is 40 mm in diameter. Pipe diameter is given. Mass flow rate of water is 1.5 kg per meter cube. Temperature at the well T1 is 283 degree Kelvin and P1 is 90 kilopascal. Temperature in the outside, that means in floor line, datum, T2 is 283 degree Kelvin. So T1 is equal to T2. Temperature is constant. A clue to solve the problem. When temperature is constant, changes in internal energy becomes 0. Right. Pressure 2 is 400 kilopascal gauge. So absolute pressure is equal to gauge pressure plus atmospheric pressure. So 1 atmospheric pressure is equal to 101.325 kilopascal. You have to add 101.325 kilopascal in order to find the absolute pressure P2. Clear? This is the problem. The question is what is the find the pump work required. The problem comes under the category of First Law of Thermodynamics for steady state flow process. The problem comes under the category of First Law of Thermodynamics for steady flow process. Steady flow process. Mathematical representation of First Law of Thermodynamics for steady flow process is changes in enthalpy del H plus changes in kinetic energy of M del V square del U square. Changes in potential energy G del Z is equal to Q minus W's. Q stands for amount of heat exchanged, WS stands for shaft work. This is a question mark. This is the question to solve the answer. Clear? Okay. Inlet and the exit, entering and exit velocities are constant. Hence, this term becomes 0. Clear? The process becomes adiabatic. Hence, Q is also 0. The remaining thing is del H plus G del Z is equal to minus Ws. H stands for enthalpy. That means del U plus V del P. V del P. PdV. H is equal to U plus PV. Volume and volume flow rate is constant. Pressure alone gets exchanged between two extreme ends. Hence, I am going to write this equation like this. That is equal to minus Ws. Okay. Temperature is constant. T1 is 283 and T2 is also 283 degree Kelvin. Changes in temperature. There is no changes in temperature. Temperature is constant. Hence, this term gets eliminated. V is the specific volume. Specific volume. SPECIC. Specific volume. That means inverse of density 1 by rho. That means 1 divided by 1000 meter cube per kg. And changes in pressure is P2 minus P1. P2 is equal to 400 kilopascal gauge plus 1 atmospheric pressure, that means 101.325 kilopascal. Clear? So P absolute, P2 is equal to 501.325 kilopascal. Again P1 is already given in your problem. Now I am going to solve the problem. So what is this? Del H V into del P, 1 by 1000 meter cube per kg into P2 minus P1. P2 is 501.325 minus P1 is 90 kilopascal. Okay, this is kilopascal. Kilopascal, pascal means Newton per meter square. Kilopascal means kilo Newton per meter square. 1 pascal is equal to 1 Newton per meter square. 1 kilopascal is equal to 1 kilo Newton per meter square. So Kn divided by meter square. Meter square, meter cube is cancelled. Remaining thing is kilo Newton meter per kg. So 1 divided by 1000 into 501.325 minus 90. The unit becomes kilo Newton meter per kg. This becomes kilojoules per kg. Kilojoules per kg. What is the answer? 501.325 minus 90. Clear? So this is 411.325 divided by 1000. So this becomes 0.411325. Clear? 501 minus 90. Okay, well and good. Right, now it is ready. What next? G del Z. G del Z. So G del Z is equal to 9.81 meter per second square into del Z is equal to 15 meter. So this becomes meter into meter square. 9.81 into 15 is equal to 147.15 meter square per second square. For simplification, I am going to multiply kg and divide by kg per kg. Clear? There is no changes in value. Clear? Now kg meter per second square, 147.15 kg meter per second square into meter per kg. Clear? Kg meter per second square is nothing but it is a joules. Newton. 1 kg meter per second square is equal to 1 Newton. So 147.15 Newton meter per kg. Newton per meter is nothing but joules. I am in need of kilojoules. Hence 147.15 divided by 1000. The unit becomes kilojoules per kg. The answer is 0.14715 kilojoules per kg. Okay, what next? Minus Ws. Minus Ws is equal to V into del P plus G del Z. So V into del P is nothing but 0.411325 plus 0.14715. What is the answer? So 5, 7, 4, 8, 5, 5. 0. The answer becomes 0.558475 kilojoules per kg. Kilojoules per kg. Right. How can I convert this into kilowatts? I am in need of watts. For that, mass flow rate of water is given. Mass flow rate of water is 1.5 kg per second. Just multiply minus Ws is equal to 0.558 4 decimal accuracy 85 into 1.5. This unit is kg, kilojoules per kg. into mass flow rate of water kg per second. Kg gets cancelled. The answer becomes 0.5585 into 1.5. What is the answer? 0.83775 kilojoules per second. Joules per second is nothing but it is watts. So the answer is 0.83775 kilowatt. This is the answer. Pump work required to pump water from a depth of 15 meter in a well to the datum level. This is the answer for this question. Clear? Ws is equal to minus 0.83775 kilowatts. That means this much amount of work required on the system, work to be done on the system in order to lift the water from well to the datum level. This is the answer. Clear? Thank you. The problem comes under the category of first law of thermodynamics in steady flow process, steady state flow process. Clear? Application of thermodynamics to flow process, application of thermodynamics to pumps. Clear? Thank you.